This video begins the questions on our review sheet related to trigonometric identities. So the first problem had a series of 4 parts. The first part of that question said suppose that the sine of our angle theta equals 3/5 and that the cosine of the angle is negative. Our task is to find the cosine of the angle and then show the angle in standard position. So we start by thinking about the unit circle. Always try to think about things in the language of the unit circle. So I've got a circle. I know that the sine of my angle is 3/5, and so I want to emphasize that the sine is the y-coordinate. And to say that the y-coordinate is 3/5 says that we are 3/5 on the y-axis. So notice that there are 2 possible locations on the unit circle that have a height, a y value of 3/5. And we're interested in the one where the cosine is negative. And so the point we're interested in is this point here. Now this actually is enough to answer the second part of the question. My angle theta is the angle that goes through the left side of the circle with a height of 3/5. To find the cosine of the angle, what we'll do is we'll use the Pythagorean identity. The sine squared plus the cosine squared of an angle is always equal to 1. And our sine was 3/5. And let me just emphasize, I'm not writing the sine of 3/5. This is the y-coordinate, theta is the angle. The sine of theta squared, 3/5 squared, plus the unknown, let's call it x squared, is equal to 1. So I get 9/25 plus x squared is 1 squared, which is 25. So we get x squared equals 16/25. My x would be plus or minus the square root of 16/25, or plus or minus 4/5. I choose the one that corresponds to my quadrant, where I choose the negative value, so that I find that my cosine, the cosine of my angle, is negative 4/5. Part B to this problem considers the same angle. So we know that the sine of my angle is 3/5, and from our previous problem we know the cosine of my angle is negative 4/5. And we're interested in finding the sine of negative theta and the cosine of negative theta. So on our unit circle, let's review what we had from our previous problem. In our previous problem, we had a height of 3/5 and an x-coordinate of negative 4/5, so that we went through this point. This was my angle theta. I arrive at that angle theta in the positive direction by starting at the positive x-axis and rotating until I reach that theta. So this is how I do theta. Well, to answer the question about negative theta, I'm going to go the same amount in the opposite direction. And so negative theta goes the opposite direction. And the thing that we need to notice is that we have the same x-coordinate, but the opposite y-coordinate. So this is the even and odd property of our angles. The sine of negative theta, the y-coordinate, is the opposite of the sine of theta. So we get negative 3/5. The cosine of negative theta is the same as the cosine of theta because the reflection, we're exactly on the same x-coordinate. We're just on the opposite side of the x-axis. And so the cosine of minus theta is negative 4/5. And so we found the sine of the angle, we found the cosine of the angle, and we've identified where the angle is on the unit circle. Part C of this problem considers the same angle theta, and it asks us to find the sine of theta plus pi over 3 and the cosine of theta plus pi over 3, and then show the angle theta plus pi over 3 in standard position. Like the previous problem, we've already done the work for the theta, so let's re-summarize what we have. So I've drawn the unit circle, and I've put the y-coordinate at 3/5, the x-coordinate negative 4/5, and now we want to consider the sum identity for the sine and cosine. So the sine of theta plus pi over 3 uses the sum identity for sine, and the sum identity for sine mixes things up, so we get sine cosine plus cosine sine. So sine cosine plus cosine sine. This is how I like to think about it. I just fill in the parts that I know. Sine, cosine, cosine, sine. So the first angle was theta, the second was pi over 3. So I just make sure that I am consistent. Notice that I always need to have the sine of theta and the cosine of theta, and the cosine of pi over 3 and the sine of pi over 3, and the sine sum identity is always the same sine. So notice we know what the sine of theta is, that's 3/5, and we know the cosine of theta, that's negative 4/5. We need to remind ourselves of the angle pi over 3, and recall that pi over 3 radians is the same as 60 degrees. It's a third of a half circle. So if I draw a 30, 60, 90 triangle, 30, 60, I always remember that opposite 30 degrees is the small side of a half, which is all I usually need to remember, that the long side, the opposite of the 60 degrees, is square root 3 over 2. So this is going to be useful for me. I now know that the adjacent, so that's the cosine of 60 degrees, is the half, and the opposite of 60 degrees is the sine of 60 degrees, or pi over 3. So I can now substitute into my formula sine of theta plus pi over 3 is going to be the sine of theta, 3/5, times the cosine of pi over 3, which is a half, plus the cosine of theta, which is negative 4/5, times the sine of pi over 3, which is square root 3 over 2. And I get a net value of 3 from the first, minus 4 square root of 3, all over 10. And using a calculator I can find a decimal value so it's easier to see on my unit circle. The decimal value is approximately negative 0.3928. So this little piece of information tells me I'm about negative 2/5 the way down, not quite. Here is the sine of my angle. And now I'm going to do the cosine identity, the cosine of theta plus pi over 3. Now the cosine is cosine, cosine minus sine, sine. So cosine cosine minus sine, sine, which I can now substitute my values. The cosine of our angle was negative 4/5. The cosine of pi over 3 we said was a half, minus the sine of theta was 3/5, and the sine of pi over 3 is root 3 over 2. for a total value of negative 4 minus 3 square root 3 all over 10, having an approximate value, our approximate value negative 0.9196, which is really close to the edge. So we're somewhere in here. And so my angle theta plus pi over 3 is in quadrant 3. So we found our sine and our cosine, and we've located our angle. The fourth part of this problem, given the same angle, is to find the sine and cosine of 2 theta. And so here we'll use the double angle formulas. The sine of 2 theta is sine theta cosine theta plus cosine theta sine theta, or 2 sine theta cosine theta. And since we know the sine of theta was 3/5 and the cosine of theta was negative 4/5, we get that the sine of the double angle is 2 times 3 is 6, 6 times 4 is 24, and negative 24 25ths, which is, wow, that's amazingly close to negative 1. And the cosine of 2 theta, we have our choice. I'll use the cosine squared theta minus sine squared theta. And so I get negative 4/5, that's the cosine, squared, and 3/5 squared for the sine. And so I get 16 25ths minus 9 25ths, giving us a total of 7 25ths. So our y-coordinate is very close to negative 1, and our x-coordinate is about a third or so. And so our point I have negative, that wasn't right, positive a third or so. So our angle 2 theta is here. Now, part of what told me that my mistake originally was wrong is if I put an angle here, that's not enough to double my angle, because I need to double, basically I need 2 of these 90 degrees, and then I need 2 of these angles, so I should be somewhere in the fourth quadrant. And so that finishes up the first problem. The second problem in this section is a proof to show that the cosine of pi over 2 minus theta happens to be the same as the sine of theta. The way that I'm going to do this is actually to use the sum identity. So here pi over 2 minus theta is the same as pi over 2 plus the angle negative theta. So that if I go and I say, okay, what's the cosine of pi over 2 minus theta, I get to use the cosine sum identity. It's the cosine minus sine, where my angles are pi over 2 and negative theta. Now pi over 2 happens to be one of our famous angles. It's 90 degrees. So the cosine of pi over 2 happens to be 0. So it's 0 times the cosine of minus theta, minus, and the sine of 90 degrees is 1 times the sine of negative theta. And so this first term doesn't even matter. I get negative sine of negative theta. And here I just want to remember that if I have an angle, negative theta has the opposite height. So I get negative sine theta, which is the same as sine of theta. And so this key step uses the fact that the sine is an odd function, which is one of our identities. So we use the sum identity, and we use the odd property of sine function in order to prove our result. From a communications point of view, notice that every step I have an equation. I have my original formula, I have it equals a new formula, and so I'm connecting each subsequent formula to the previous formula. And a proof needs to be something that step by step, every statement needs to be a statement, an equation basically for this, and we have a good proof. The third problem in this section is to find an exact representation of the sine of 5 pi over 12. Now every time that we have a problem like this, especially where it's an angle like a twelfth of number of twelfths pi, the idea is we just want to think about basic angles that we know and see if I can combine them to get the 5 pi over 12. So the most common ones that we work with are the pi over 6. These are the only ones we're really expected to know. Pi over 4 and pi over 3. So this is the 30-degree angle. This is the 45-degree angle. And pi over 3 is the 60-degree angle. And so if I think about those in common denominators, I guess I'm not doing conversions, these are equal to 2 pi over 12, 3 pi over 12, and 4 pi over 12. So that when I combine 2 pi over 12 and 3 pi over 12, I get 5 pi over 12. In other words, the question that I'm wanting, the sine of 5 pi over 12, is a sine sum identity where I'm taking the sine of pi over 6 plus pi over 4. So I use the sum identity where I have sine cosine plus cosine sine. So it's pi over 6, pi over 4, pi over 6, pi over 4. Just an observation again. Notice that we have the sine and the cosine of each angle. Cosine pi over 4, sine pi over 4. Well, either I remember these sines and cosines, or I simply redraw little triangles to remind myself. If I have a 30, 60, 90 triangle, remember the narrow angle is 30 degrees. The opposite side of 30 degrees is the short side of a half, so that I can get that the cosine, the adjacent side, is square root 3 over 2. And the 45, 90 triangle, it's isosceles. And if you can't remember what it is, you can always say, well, it's isosceles, so x squared plus x squared equals 1. 2x squared equals 1. That means x is the square root of a half, which is root 2 over 2, or 1 over root 2. So as I go in and use my values, the sine of 30 degrees, or pi over 6 radians, is a half. The cosine of pi over 4 is root 2 over 2. The cosine of pi over 6 is root 3 over 2. And the sine of pi over 4 is root 2 over 2. So that I get an exact formula for the sine of 5 pi over 12. It's root 2 plus root 6 over 4. The last question in this section of the review problems is to find an exact representation of the cosine of pi over 8 and the sine of pi over 8. To answer this question, we recognize that this is actually half of an angle we know. So pi over 8 in particular is exactly half of pi over 4, which can alternately be thought of as saying as pi over 4, an angle we know, happens to be the double angle of pi over 8. Now, among the formulas that you're told that you'll be given are the double angle formulas, that the cosine squared of an angle x is equal to 1 plus the cosine of the double angle divided by 2, and that the square of the sine of an angle is always equal to 1 minus the cosine of the double angle over 2. And so this is how we're going to be able to take advantage of this. If I think of x equal pi over 8, then what this tells me is that the square of the cosine of pi over 8, which is what we don't know, this is always equal to 1 plus the cosine of double that, which is pi over 4, all over 2. And we know that the cosine of pi over 4 is root 2 over 2. So that I can get 2 plus root 2 over 2. Then I still need to divide it by 2, so I multiply by a half. So what I find is that the square of the cosine is 2 plus square root 2 over 4. Similarly, the square of the sine is 1 minus the cosine, so I meant to say, of pi over 8. It's 1 minus cosine of pi over 4 over 2. So we get 1 minus root 2 over 2 over 2. It's similar sort of algebra. It's going to give us that the square of the sine is 2 minus root 2 over 4. Now I want the cosine and the sine, so I take the square root. The cosine of pi over 8 must therefore either be plus or minus the square root of 2 plus root 2 over 4. If I think about where pi over 8 is in the unit circle, I'm going to choose the positive square root. So because based on the quadrant, it's 2 plus the square root of 2. The square root of 4 is 2. Similarly, the sine of pi over 8 is also going to be positive. It's the square root of 2 minus square root 2. Square root of 4 is 2. So this finishes up our last problem on this section.